I'm an associate professor at Simon Fraser University. I work on a variety of topics related to digital twins. The title of my talk today is Towards Realistic and Interactive 3D Simulation for Embodied AI. And I'll begin by trying to explain this title and its connection to digital twins. So firstly, this first half of the title, 3D Simulation for Embodied AI. What do I mean when I say that? I mean these kinds of simulated experiences inside interior environments, navigating in real spaces, interacting with real spaces, rearranging objects in them for a variety of applications, such as, training robotic agents, embodied AI agents, and so forth. So you see here the connection with digital twins of interiors, essentially, doing these kinds of simulations of experiences for navigation, manipulation, and so forth can benefit a lot from having highly detailed digital twins of interior spaces. Now, this is, of course, not a new topic. There has been much work in, across the years. And I'll take a bit of a historical detour to motivate some of the context for this presentation by saying, my personal entry into this area. How did it happen? Around 2018 or so, I saw, like many others, an explosion of interest in this type of simulated experience, particularly inside indoor spaces. Here, it's definitely not an exhaustive list. It's just a few works that happened at the time. All of them focused on leveraging these kinds of simulations of, rooms, houses, and so forth for a variety of purposes. And it's not really a surprise that there has been much interest in this over the years, because many research communities benefit from these kinds of simulations and from the underlying, realistic representations of indoor spaces. Communities that are interested in visual navigation, robotic grasping, grounding natural language in, real world spaces, following natural language instructions, mapping instructions to actions, dexterous manipulation, and so forth. Many, many examples of these kinds of, downstream applications for simulation and for digital twins. So now coming back to the title, I'll drill down a little bit into two specific parts in this presentation. And the first part that I will focus on is this, word here, towards realism. I'll motivate what I mean by this by setting up a little bit of a problem, again, going back to the historical context of how, the dominant paradigm for doing these kinds of simulations of interior spaces was, how it was back at the time. So a very common strategy was to take a black boxed 3D game engine and the content that comes with that 3D game engine, and then set up some sort of useful tool for, researchers to navigate, let's say, in a house and interact with objects. And here's just an architectural sketch of what that would look like. You take something like a Unity game, write a little Python wrapper around it, and then allow it to interface with PyTorch. Sometimes even by simulating, keystrokes and mouse clicks that go directly into this black boxed game engine. And, this is a bit of an interesting way to go about it, because, the original component here, it was designed to be used by a person with a monitor, right? And a mouse and a keyboard. So a very different use case. Compared to how we want to use it with these simulations, where the purpose really is to generate lots of data, high throughput kind of data generation in a variety of modalities, not just the RGB pixels that will get displayed to a monitor, but other useful modalities too. Depth information, surface normals, simulated LiDAR sensors, etc., etc. So, having given this context, I mentioned that this is, around that period of time, around 2018, 2019, this was my entry into this area. I was involved in the Habitat project, which was an effort to try to leverage relatively higher fidelity reconstructions of interior spaces rather than these black boxed game engines and the content that came with them. And so the goal was really to make it possible and also efficient for researchers to do these, simulated, navigation and manipulation experiences in realistic interiors. And with a little bit of care, this could be done efficiently as well, unlocking, speed that is useful for high volume data generation. Now, a big bottleneck at the time, and even still, is that this kind of work that relies on reconstructions of real spaces from the real world is limited by the volume of available reconstructed spaces, right? And there are actually, to this day, relatively few house scale, high fidelity reconstructions of spaces. The visualization that you see here comes from the Matterport dataset that was used as the source of data for the Habitat project. Each of the green dots that you see there is a placement of a tripod used to scan the house. In order to scan a house, you can imagine how much effort is required, right? To go around, put a tripod down, scan, right? And then eventually acquire this detailed 3D mesh representation of the space. So it's quite effortful. It takes time. It's a little bit hard to scale, right? And therefore, there's not that much data. So what can we do about this, right? This is one of the motivating questions for this presentation. And the structure of the remainder of the talk will be a quick journey through a variety of recent projects in the last year or so that try to tackle this challenge of the limited availability of the data, essentially the digital twins of interior spaces. I'll begin by talking about this project at the top left here, HSSD, which was presented at last year's CVPR. And the goal of this project was to collect a realistic data set of synthetic interiors that you see visualized here. Synthetic interiors of a number of houses, and in particular with the focus being on, detailed, richly populated interiors. So to give you a little bit more of the statistics of this data set, this was composed of 211 houses modeled by professionals. And these houses are constructed compositionally from a library of 18,000 or so unique objects, from a number of different categories of objects. And one of the important details is that due to this compositional construction from a library of objects, it's relatively easy to have detailed semantics, right? To be able to say, okay, here is, a view in this interior. These are exactly the kinds of objects that I'm looking at. Semantics like instance level segmentation masks and so forth. Examples of which you see here on the right. Now, I mentioned semantic realism for this data set, and what does that really mean? When I use this terminology, I mean, similarity to the real world patterns of object arrangements, right? The kinds of objects that you observe in indoor spaces and how they are positioned relative to one another. This was a focus of this particular project. And to kind of characterize this, we used as a proxy the statistics of how objects co-occur in real world spaces. So for example, if you go to a living room, you might see that there are usually, TVs, and near those TVs, there might be couches, or there might be, dining tables and so forth with chairs around them. So these common co-occurrences of different object categories, they characterize really the semantic patterns of indoor spaces. And a good way to maybe strive for realism is to try to make synthetic data match the real world patterns. That's the general idea. So the way that we try to summarize this is to compute, pairwise co-occurrences between categories of objects. You see them here summarized as, heat maps, where each row and column represents a particular category of object, and then more saturated color indicates higher, frequency of observing those two categories together. And really, the details here are not important. It's more the general trends, the contrasting, prior work on synthetic data with this particular data set, the HSSD data set, and then comparing it to reconstructions of real world spaces. So if you squint, you can sort of see that the middle heat map here for the HSSD data set is more similar in aggregate to the one on the right, indicating that it's in closer alignment with the co-occurrence patterns of the real world. So that's the general idea. And in this work, a particular goal was to see, does this realism help in some concrete way if we want to use this data for training? The particular context was embodied AI navigation agents. So the experiments in this work trained navigation agents in the synthetic data and then deployed them in these reconstructed interiors to see zero shot how well they generalize. Again, I won't go too much into the details. I'll briefly show some plots here. And then the key point that I'd like to make is that with a very modest scale of this kind of synthetic data that is more well aligned to the statistics of the real world, generalization performance is significantly higher than much, much more synthetic data that doesn't align so well with the real world. That's really the takeaway from these experiments here. That was, the HSSD project, which relied on synthetic 3D scene data sets. But we still haven't really solved the problem of, data volume because, this was a data set of 211 houses, and the process that went into constructing these synthetic data sets is highly laborious. Here you see a sped up video of someone putting together one of these synthetic scenes using a design interface. And it's no easy task. It actually takes quite a bit of effort to put together a realistically populated 3D scene. It's a lot of manual effort. What can we do about that? That's the focus of the other, the next project that I want to talk about, Scene Motif Coder, which was presented at this year's 3DV a few months back. And the goal here is to algorithmically generate these arrangements that constitute realistic 3D scenes. So to motivate a little bit this particular work, there's of course quite a bit of prior work in this area, right, to generate 3D scenes, 3D layouts of objects. But one observation that this work made is that a lot of the prior work, in fact, pretty much all of it, focuses on these relatively large objects, furniture pieces, and so forth, tables, cabinets, and very little on smaller objects, plates, bowls, utensils, things like that, leading to generated scene arrangements that are unrealistically empty. They don't feel like lived-in environments. They don't really have rich detail. And this is, of course, due to a number of challenges. One of them is that this kind of detail is rarely captured in scene data sets at scale. These kinds of arrangements of smaller objects are highly compositional and also typically in very tight geometric contact. So generating plausible arrangements of these kinds of objects is actually quite challenging. How did this Scene Motif Coder project try to approach this? It leveraged two key ideas. One is that it's possible to learn from a relatively small number of examples some structural patterns that we call motifs that characterize many of these arrangements. So for example, if we had this kind of arrangement here, a stack of 7 plates, a user gave this to us, right? They said, here's a stack of 7 plates. This is what a stack means. We could perhaps try to extract out of this an abstraction of this arrangement, a representation of it, so-called motif, that this is what it means to stack objects, right? Objects that are stacked are vertically on top of each other. And with this abstraction, we could perhaps hope to be able to generate many, many possible variations of this type of arrangement, right? A stack of other things, a stack of books, a stack of towels, and so forth. That's one key idea. The second key idea is that these structural patterns, the motifs, are actually captured very well by programs, by code. The structure of code is actually a very good fit for the structural patterns of objects in these tight arrangements. So for example, for loops that iterate and place object by object, vertically one on top of the other, can very well represent the structure of motifs. And by representing these motifs as code, we can then, hope to perhaps be able to apply this code in a very general fashion by executing code with different arguments to produce new arrangements, like the one that you see here, the stack of book, filling in, the appropriate variables, book, 4, get a stack of 4 books. So that's pretty much it. I won't really go into the technical details of the implementation, other than to say that it's a framework that, as you might imagine, leverages a variety of recent large language and vision language models, and goes from these kinds of examples that are given at learning time to produce a library of metaprograms, and then uses that library of metaprograms at inference time to retrieve an appropriate metaprogram, to fill it in with the appropriate arguments, and then to generate the desired arrangement of objects, such as the stack of books that you see on the bottom right there. And yeah, of course, all of this is powered by advances in large language models. I'll very quickly go through some of the, just at a high level, the qualitative results, comparisons with the work that either directly tries to generate these arrangements from a text description, or similarly tries to compositionally retrieve assets and put them together. And the general point that I'd like to make is that this kind of approach that it uses programs to represent the arrangements is much more reliable in matching constraints specified by the input, the number of objects, the exact spatial arrangement of the objects. And you see that here, for example, in the second row, stack of 3 towels. Most of the other approaches don't really do a good job of having the appropriate number of towels and realistically stacking them on top of each other. So this general approach allows for putting together richly detailed scenes. And, the general idea is, after we've learned, some number of these motifs, structural patterns, we can compositionally put them together to populate the scene, such as in the example that you see here of a table that's prepared for a birthday party. Another advantage of this approach is, since code is really the key, the representation here, these meta programs, these are also human readable and human editable. So a user could come in and say, let me adjust this particular meta program, this motif, and now make it into a stack plus an extra object of a different type on top. So a stack of plates with a mug on top, and so forth. That's another advantage. So moving along, I'll just very briefly mention some very recent follow-up work on hierarchical scene motifs, extending this idea to larger scales, to whole rooms. It's pretty a straightforward application of this idea of motifs, where now we apply them recursively. At the level of the whole room, capture these patterns and try to represent them as programs, lay out the dining table and the chairs, and then proceed to support surfaces, and again apply this idea of populating them with various motifs, and in this way recursively populate the scene. And also very briefly, I'll just advertise here another related work that is appearing at this ICCV, presented by Thierry, actually, who's one of the organizers of this workshop, on zero-shot single-view 3D scene modeling using large vision language models, foundation models. So this is another strategy to try to alleviate the data bottleneck, and to try to go from a single view observation of a scene to a synthetic proxy, a digital cousin of that space. Again, the idea is to, as I mentioned, leverage recent VLMs in a zero-shot fashion to detect objects, retrieve synthetic proxies for them, and arrange them into a realistic-looking 3D scene. Check out the poster tomorrow in the afternoon, and number 364, if you want to learn more. So that was the first, half of projects on realistic, and now I'll focus on the interactive direction. So what does this interactive mean? Everything that I've shown so far is essentially completely static, completely frozen in place. All of these considerations about digital twins and data are not taking into account the dynamics of these scenes. So none of these nicely realistic, reconstructions or even synthetic data that I showed allow for, dynamics like opening the doors, moving from one room to another, interacting with the appliances, opening microwaves and so forth. And that's a shame, because really interaction is where it gets tricky, where we really need to be able to simulate what happens when an embodied agent actually interacts with the environment, as this infamous example from the DARPA challenge demonstrates. Even opening doors is a non-trivial task, right? So an early attempt in this direction from a number of years back was to collect 3D scenes using reconstruction in multiple states, and then thus characterize the articulations of common everyday objects. So this was a dataset effort relying on reconstruction called Multiscan from a few years back. Check it out if you're interested in this direction of reconstructions with dynamic information annotated. For the rest of this presentation, I'll focus on synthetic data though, again. So synthetic data for interaction, with articulated objects. And first, this S2O project, where the key motivation is to take a static 3D object and then make it into an interactive object, make it an object that can articulate, that we can open and close. And the broader, motivation is that we are having, increasing amounts of these static synthetic assets. Wouldn't it be nice if we could take all of those and make them interactive algorithmically, right? Take each of these static objects and then have it, have parts that can move, that can be interactive. That really is the broader motivation of this project. And, it was mostly a benchmarking effort where we tried to break down this task into important subtasks and see where does the state of the art lie in these important subtasks to go from a static to an interactive asset by looking at the various representational choices that one can make, also choices for how to do segmentation into movable parts, choices for how to do prediction of motion parameters, articulation parameters, and also choices for how to complete missing geometry. One key issue with these kinds of static assets is that they often do not realistically model the interiors of the objects. So as I mentioned, the focus was on benchmarking. So this project contributed a data set of fairly detailed articulated assets to provide some ground truth, and then compare various approaches for those subtasks that I described earlier. It's only a first step. I won't really go into detail in the experiments here. I'll refer everyone to the paper if you're interested. Many challenges remain. That's the takeaway message that I want to give. I'll very quickly move on to the last part, which is motivated by this question. What if we don't even have, enough of these, synthetic static 3D objects? Even the process of designing a single 3D object, a richly detailed object of that conforms to what we might expect in the real world, is fairly laborious. Here again, you see one of these sped up videos of a professional trying to put together a bed. So what do we do then? Here we can maybe leverage advances in generative models to try to generate from scratch, essentially, a realistic, interactive, articulated object. This is a project from last year's CVPR called CAGE on controllable generation of interactive 3D objects, where the input is a high-level specification of what type of object we desire, a storage unit, how many parts should it have, and how should those parts be connected, represented by this input graph on the left. And the output is in the far right, the geometry of the object, its articulation parameters, so that it can be, directly interacted with. Again, I won't go into the details. The key idea here was to use a diffusion approach, as is popular, and represent these objects in a tensor format, where really the contribution was to design a set of specific attribute attention blocks that leverage the kinematic structure of articulated objects to pay attention to appropriate parts and therefore determine the parameters of articulation reliably. So very quickly, I'll go to the qualitative results, showing here some out of distribution, in quotes, graphs, number of parts that were not observed in training data. You see again in the first column the input, and then in the pairs of columns to the right, you see generated objects that conform to that constraint of that category and that number of parts. And a related, more recent work from this year's iClear was tackling the image condition version of this problem, where we now have an image that we want to match, and we all again want to have the detailed geometry and articulation parameters of that object. So it's very similar in spirit to what I just described. The only difference is that now we use the input image to condition the generative model such that the geometry and the articulation parameters are ones that are informed by what we've observed in that single view of the object. And this is done using a cross-attention module that leverages image features. So again, won't go into the detail. 1 minute left. Okay, almost done. Won't go into the details. I'll just briefly show some examples of image inputs in the first column, and then in the next two columns, a generated object that comes from that image. Also some examples on internet images, microwaves, storage units, and so forth, to demonstrate that this is something that can be applied, to data in the wild, in quotes. So that was pretty much it, a very quick journey through a few recent projects that try to tackle this data side of 3D simulation and constructing digital twins. A few quick takeaway messages. It's, of course, very useful to be able to simulate realistic interiors, but really, to unlock the potential of this set of tools, we need to work on having more realistic and more interactive data, the digital twins that we can put together to power those simulations. To go towards more realism, it's worthwhile to investigate methods for 3D scene generation that can scale and that can richly populate the environments in compositional ways across spatial scales. And then to go towards more interaction, it's worthwhile to investigate methods that can allow for controllable generation of articulated objects that we can then compose together into interactive scenes. So that's pretty much it. All of this work was done, of course, by great students and collaborators. I have the benefit of being in a collective of researchers that is very vibrant, very energetic, the SFU Visual Computing and Research and Robotics Lab. If you're ever in Vancouver, come visit us, say hi, we're happy to have you. And I'll also very briefly advertise that next year's conference on 3D computer vision is in Vancouver. If you're interested, check it out. It's going to be in March. And I'll end here by thanking all of the students and great collaborators who make this work possible. Thank you all.
I'm actually the one of your questions. Feel free to choose them.
Yeah.
I want to ask you, when we want to do a scene simulation, do you think that we should go from this coded interface that you said, that from text directly to code, directly to instantiation of the scene? Or do you think that we can exploit text to image that is very mature and then going from image to 3D? So different pathways, or maybe a mix of two. I'm not sure.
Yeah, that's a great question. Oh, thank you. Yeah, thank you so much. Yeah, that's a great question. So these two paths, right? Going from, let's say, some textual description of what we want, or going from code to what we want, right? Those are both valid. One thing that I didn't describe actually is that this work that is being presented at this ICCV here, diorama that Chiro is going to present as a poster tomorrow, explored both paths. Right, relying on an image to go to a digital twin, digital cousin of the scene, but also trying out leveraging of text to image models. Right, take a text description, construct an image of that scene, and then take that image to go to the digital twin. So there's actually bridges that can be established between these paths. Right, we can go from text to a generated image, and then hook it up with an image conditioned approach. And there's possibly also bridges where we can go to text to image, image to code, and then code to a twin. And there are trade-offs there, I think, in how to put things together. Yeah.
Directly to a code that generates this. Do you agree?
Yes, yeah. That work was text input. Yes. From text input.
Generated or real when we make a scene? Because it needs 4,000 words, let's say. Or we go directly from text to code. to the scene without going through the image.
Yeah. Now I get the distinction. Yeah, that's a great question. I think it depends. For the kinds of, highly compositional arrangements that I was showing, maybe it's not necessary to have this intermediate that goes through an image, right? Because one problem here is that some of these are very mundane kinds of things that I imagine, whatever text-to-image model you might want to use, there's many challenges to get, like this detailed, realistic, kind of highly cluttered, compositional, arrangement of objects. So that path may be not ready to be an intermediary, and it's okay to go through this abstraction of a code level representation of how objects go together in these very local arrangements. So yeah, for the moment, I would say maybe we can skip the text to image for those kinds of specific arrangements. Yeah. Yes.
Yes. When generating synthetic scenes, how do you weigh up the balance between capturing all possible combinations and what are the most likely arrangements of scenes, right? Realism in terms of physical possibility, also likely combinations of the dining room. How do you get to the point that you can train a detector, and if you put a chair on the table, you can still detect it?
Yeah, that's also a great question, right? There's this notion of plausibility versus likelihood, right? And then likelihood is something that has to do with the real world, right? Is this a likely arrangement in the real world? Is it something that, if you cared about detection in the real world, right? Probably having it be a likely arrangement is more useful than just having it be plausible, right? And very unlikely. So I don't have a good answer to this. I think the project that I described in the beginning, HSSD, tried to characterize this likelihood as this very simple abstraction of co-occurrences of categories in physical proximity, and then say, okay, if we can get the co-occurrences to be, more similar, then we have higher likelihood for being a real world arrangement of the same type, right? But I think there's a lot more attention that should be paid to this question. Yeah.